Okay. Yeah, so last time we were talking about System F and church encodings and that stuff. I want to mention one thing really quickly, which is that there's this conference, ESEC/FSE is what it's called, which is a very catchy name. Anyway, it's actually a software engineering conference. It's not programming languages specifically, but they have lots of cool stuff. And there's a YouTube channel where you can just like see all the talks. So if you see anything that looks cool, you can check it out. Yeah, so I'm just going to show this in the chat. Encourage you to take a look for cool things. The chat, which does not seem to be opening. Well, let me. Okay. There. I'll stop sharing because apparently that's the only way to see the chat. Anyway, so here's these links. If you're, yeah. Anyway, yeah, there's a lot of different topics. There's like testing stuff and verification, analysis stuff, and I don't know, some machine learning too or something, if you're into that. Anyway, so back to the topic of the day, or the recap of the topic of the day. So anyway, System F, if you recall, is basically like the simply typed lambda calculus, but with parametric polymorphism, meaning that you can have these functions that are parameterized work for all types. So like this identity function for all alpha, given an alpha returns an alpha. Something that you can't write in a simply typed lambda calculus, but now we can. We have, so yeah, here's the syntax. Again, the same as simply typed lambda calculus, but adding type variables and these for alls, the quantifiers, and then adding the type abstraction and type application expressions. And then for the evaluation rules, we had the same rules as before, but adding the type application rule, app_ty, and then we added 2 new typing rules for type abstractions and type applications, which are below, and hopefully vaguely recall. But we're switching topics, so even if you don't, you will not be lost for long. Let's see. Yeah, we talked about Booleans. So we had Booleans before in lambda calculus. We had to add them in as a special type in simply type lambda calculus, and now we get them back. It's just a thing we can define in the language. So these functions that take in 2 arguments and either return the first thing or return the second thing, ignore the other argument. It works just like an if statement, and you can make and or and not and etc. out of these things. Yes, and we briefly talked about pairs. So here's this pair definition, and what a pair is in System F, or one way to encode pairs in System F, is as these functions. So they take in 2 arguments and sort of hold them, in standby, so to speak, until you give them that a function that will use the 2 arguments you provided. So when you give it the function gets both of the values from the pair and can do whatever it wants with them, and that's pairs basically. So we have these first functions and second functions, and all it does is it takes in some pair. So for all types alpha and beta, oops, should be a lambda. That should be a lambda too. It takes in some p, which is a pair of alpha and beta, and then we give this pair this function, which takes x and y and returns x, and then second takes x and y and returns y. And if you evaluate these things, as I do here, you will see that it works just like first. I'm not going to like step line by line through this because it's pretty gross, but you can follow it if you want. It really does give you 4 if you do it all the way down. Yeah. Anyway, last thing I want to talk about before we move on to Featherweight Java is lists. So before, we had to talk about adding pairs and some types and all these things. We could have done lists in that same way by making another special case of lists. But in System F, we can actually define lists ourselves, again, in the language, because the type system has much more power than before. So if we recall our sort of rule or maxim for defining these church encodings, you define the type to be how you use the values of that type. So with pairs, it's a function that takes two arguments that are just the things in the pair. For Booleans, you use them as an if statement. For lists, you use a list as a thing to iterate over and like compute some result, basically. That's like the most general use of a list, is to use every single thing in the list to compute something. So if you're familiar with Haskell or whatever functional programming languages, you may have heard of folds. There's also something called reduce. The idea is basically you use some function, here it's called f, to combine every element of a list. So I'm not going to go in super in depth about that definition, but for example, if I do fold r, say I have a function called add, which just adds two numbers, 0 and a list x's, then this is like summing this list x's. So it just takes everything in the list, so like 1, 2, 3, and then it gives you 1 plus 2 plus 3. That's what fold does. If you expand out the definition above, you'll see. So we can do the same thing in just plain system F with a little bit more work, because we have to have all these type annotations. But fundamentally, the idea is is a list implements fold R over itself, so to speak. So for example, if we have nil, the empty list, so the type of that is for all alpha, it gives you a list of alphas, which is, I guess, what you would expect, because you can always make an empty list of anything. And the way that it works is, so, given these two types, alpha is the type of the things in the list, beta is the return type. So like here, it'll be init, or the type of init. And then you take some function that lets you combine elements of the list, alphas with betas, your current intermediate result, and then the initial value x, and then it just returns x because there's no values in the list to actually fold. Cons is longer, but it's still the same fold idea. So what it does is it takes an x, which is an element of the list, it takes x's, which is a whole list, and it puts them together. And the way it does this is by returning a function that, given some f to fold over this whole list, you apply f to x, and the result of folding the tail of the list with the initial value y. So y is init, but I didn't write init because I didn't have enough space. Anyway. It was very quick, but let me know if it doesn't make sense. And then here is the sum function, the same thing I was talking about above with fold_r add 0 x's. So it takes in a list called x's, a list of natural numbers. And then I use x's with this function here, which is add, basically, to add everything up, and the initial value is 0 because some of the empty list is 0, and then you can add 0 without changing anything.
Wait, can you back up a bit and
Sure.
refresh what's the definition of this lists type? I'm trying to understand.
Oh, sorry. Yeah. Okay. Yeah. So the list type is, so a list of A's. This is just an abbreviation. A list of alphas is basically the type of fold. So beta is the type that you're going to get out of the fold. So if you're summing, a bunch of numbers, you'll get a number, but you could do a fold that's like check all the numbers are, positive or something, and then you get and then beta would be like Boolean or something. And this thing is the function that you're folding or reducing by. So it takes alpha, which is one element of the list, beta, which is your current result, and produces a new result, which is also a beta. And then, given a beta, which is your initial starting value, it will go through each element of the list, combining the alpha and beta to get a new result, and then a new result, and a new result, etc., until it gets to the end of the list, and then that beta is the result.
Okay. Yeah. Okay, that makes sense.
Yeah. So here, I mean, so in this, some example, everything alpha and beta are both natural numbers, but it could be other things, of course. So I also put, I tried to put an example here and then went off the page and I was like, this isn't really worth it. So, but there's a little bit of it here. Basically, the idea is we're evaluating, if we had a nice language like Haskell or something, it would be like this. This is what we're doing. We're doing sum of 1 and 2. And the way that it works is by expanding things out. So what you end up with is 1 plus 2 plus 0, because that's the default value that we picked here. Yeah, I don't really want to go too deep through this again, because it's very not confusing, but just a lot of symbols. And anyway, we're going to move on to a different topic. So, but I'm happy to answer any questions if you guys have them. Anyway, so now for something completely different, Featherweight Java. So it's called Featherweight Java because it's like Java, but a very small subset of Java, which is basically the smallest interesting part of Java. So what I mean by that is it has a lot of the important features of Java. It has classes, it has methods, it has fields, it has inheritance, which is really one of the big things that it has. But it doesn't have generics, it doesn't have built-in types, it doesn't have access modifiers or interfaces or abstract classes or any of these other Java things that we all know and love. But that makes it pretty understandable, because a full Java definition would have hundreds of type rules and very confusing. So we have this grammar down here. We have 4 different kinds of things. We have class definitions. So class with some name C extends another class with some other name. It's not supposed to be the same name. I was just saying this is a class name. And then it has a bunch of the fields. So that's this part. So this line over the top means it's a list of these things. So it's like a, where should I write this? So it's like C1, F1, C2, F2, etc. So you can imagine it's being like int X, int Y, etc. Those are the fields. It has a bunch of M's. M's are methods. M's are methods. So they have a return type C, a name M, a bunch of arguments, and they return just one single expression. So the other thing that Featherweight Java doesn't have is mutation, which is you would think a pretty big part of Java, but not technically necessary and makes the language much simpler. I'm at argue that's not really Java anymore, but well, here we are. So these expressions are, so E is the expressions. These are the things that can appear in method bodies. So we have just variables, we have field accesses, we have method calls, we have constructors, and we have casts, which are very important because otherwise you can't really write a whole lot of programs in this language. And finally, the last thing is a program. So program is a bunch of class definitions followed by one expression, which is the sort of the main of the program. It's a thing that you just start evaluating, and you can call into other methods, but that's where it starts. So here's a pseudo program in Featherweight Java. I say pseudo program because there's all these dots everywhere, but if you just ignore them and pretend, because we all know what integers are, then hopefully it will make sense. So one of the other, potentially glaring omissions is that there's no if statements. But that's fine, because we can define if classes, which do the same thing. So this is using basically the same idea as the church encoding of bools, in that this if class has one method called if, and it takes 2 arguments. So this if represents true, and this one represents false. So if it's true, it takes 2 things A and B and returns A. That's the then branch. And if it's false, then it takes 2 things A and B and returns B, which is the else branch. And if you'll notice, if false extends if. So if I have something of type if. It could be if, which is the true one, or if false, which is the false one. And then integer, I decided it has these methods, but you can imagine having whatever other methods. So you can subtract, you can multiply, and you can check if it's 0. And if 0 returns an if object, which will go down the true branch if the thing is 0 and down the false branch if it's not.
Wait, quick question. How do you actually write if 0? Like, how would you actually write that without actually using a conditional?
Yeah, so it would depend on how you have it encoded. The real way you'd probably do integers, you'd have a 0 class and a like non-zero class, and then they would both inherit from integer. And then in the 0 class, for the if 0, you return the if true, like new if true, and then in the non-zero one, you return the if false.
Yeah, okay, that makes sense.
Yeah, so I don't want to write that, of course, but yeah, that's how you do it, or one way to do it. But we're just going to pretend we have integers because that's not really the point. Yeah, and then we have this class that I called main. As you know, everything has to extend something. So you can just extend object by default. Object's the only like special built-in type. It doesn't have any fields or any methods. It's just like a thing. Which is, I guess, not how object is in real Java. But anyway, so this function computes the factorial of some integer. So what you do is, so if x is 0, then you return 1. And if x is not 0, you return this, which is just x times the factorial of x minus 1, but using method calls because we don't have operators. So if you were to run this program, you would get 720, sort of, if you had real integers. It would be some ungodly mess of like new constructor calls in reality, but spiritually be 720. And then the only thing I want to technically mention is that this program actually needs a lot of casts because this language ended up being very cast heavy. So if you notice, this if method takes objects, but I'm passing in integers. So I do technically need to cast it to object, but I will not for space reasons. And then the other problem is that technically the way this function is written right now, I would evaluate both arguments until they're done, but that would involve calling factorial again, regardless of if it's 0 or not, and then calling it again and again and again and again. So what you actually need to do is have another class that represents like a computation to be done, and then when it gets returned from the if statement, then you actually evaluate it. So you don't actually evaluate the arguments until you choose which one you're going to evaluate. But that's also more space. We're going to do a simpler program that's actually like a complete program, but this is maybe like a useful program. It's also notable because we use recursion here, which is something that you can't do in System F or in the simply typed lambda calculus. It makes Featherweight Java Turing complete, which is nice because it's the first language we've had that's Turing complete other than the untyped lambda calculus. So that's also notable.
Wait, so to clarify, the reason this doesn't work is because it's strict evaluated, and so it'll cause infinite recursion.
Yeah.
From understanding. Okay, cool.
Yeah. Yes. So here's the sort of big ideas of Featherweight Java. Featherweight Java is abbreviated FJ usually because Featherweight Java is a lot to write. So yeah, one important thing we have is we have declarations, which is how like real programming languages work. Because in System F, everything is just one huge expression. Now we actually have like class definitions, method definitions, and all these things, which is much closer to how real programs work. We have inheritance and casting, which means that now we can write basically any program. You just have to cast sometimes between object and whatever type you actually want. But the inheritance means that some of the casts we can say like, oh, this one is definitely safe, or this one, is possibly safe. And then, yes, so the type soundness or type safety theorem is more difficult to state in Featherweight Java, but is again more similar to how real languages work in that Unfortunately, you don't always have this perfect, like if this program is well typed, then it just evaluates. Sometimes you can get stuck, or you can have exceptions. In this case, you can get stuck at bad casts, but that's the price you pay for turn completeness, basically. And yes, so I said it's like completely different from lambda calculus. It's not really true. If you look at it in sort of a very blurry-eyed way, it really is basically just lambda calculus, because all these methods are, they take arguments and they return an expression. So if you have a bunch of, it's basically just like a bunch of lambdas, each lambda takes an argument, returns an expression. The difference being there's declarations, but if you had in the infinite lambda calculus, it's really basically the same thing. Let's see, I mentioned this already, but everything is a subclass of object, like in real Java, I guess except for the primitives. So object gets special treatment, but it just doesn't have methods or fields. It's just there for like uniformity of the syntax. You don't have to say, well, does it extend something or does it just extend object? It's just uniform. Yeah, no statements and no mutable environments. So we can talk about languages that have mutable environments at some point. If you're interested, it's actually a huge pain to do these things, especially if you have like a stack and a heap, you have pointers and stuff. But yeah, if you're interested, we can do that. We can talk about that at the end, unless you feel very strongly now. So yeah, now we're gonna start talking about the formal definition and the rules for the language as we did for the other languages. So in addition to before, we had evaluation and we had typing. Now we have a new thing called subtyping, or a new kind of judgment. So C is a subtype of D is what this means, which really is just sort of either it inherits from it or it sort of like transitively inherits from it somewhere up the tree of classes. And the other thing to note is that, so we treat declarations as judgments. What that means is I'm going to write in the premises things like this. So class C extends D as like a premise. That just means that there is a class definition that looks like this in my program. So this is a pretty common way of doing this. The other way you could do is you could have like an environment of classes or something, like kind of like we have type environments, but that's more useful when environments actually, when the definition environments like change. This is more useful or easier to write because it's always the same. So these rules or these premises, basically, when you like type check a program, you take all the class definitions and you like stick them into the like global environment, and this is how you look them up, so to speak. Yeah, so we have these two rules that are sort of structural things. So we have subrefl, so subtyping is reflexive, so you're a subtype of yourself. And then subtrans, which is transitivity. So if C is a subtype of D, D is a subtype of E, then C is a subtype of E. And then finally, we have the one that actually is sort of language dependent, which is the sub extends. So if C extends D, then C is a subtype of D. That's basically the definition of subtype. So subtyping. Okay. So yeah, so before in the lambda calculus, we had, or simply type lambda calculus, we had sort of Booleans as values and functions as values. Now our values are like constructors. They're constructor calls where all the arguments are fully evaluated. So basically, we're treating these constructor calls as pairs or tuples of however many of all their fields. So it's like a named tuple, basically. And yeah, so you don't like implement a constructor. The constructor is just saying what all the values of the fields are. So that's what the primitive constructors are. We'll see that soon. So the way that it works is basically all these things, field accesses, casts, and methods operate on these constructor values, and they use the values of the fields. So for example, so here's this first rule, E field. So looking at a field in some constructor or in some value. And the way it works is So we say the fields of C are this list, so D, F, so like D1, F1, D2, F2, etc. And then we're looking at field I, and that gives us value I from the from here, from the list of values in the constructor call. And then, yes, so then the next rule is the cast rule, which doesn't do anything computationally, but it essentially checks that the cast is okay. So if C is a subtype of D, then we can cast C to D, and all that does is it just doesn't do anything to C. It's just checking that the cast is safe, basically. So if I have, like, let's say I have a string and an integer, I can cast like my integer to object, but I can't cast it to string. So if I try to cast it to string, it'll get stuck here because string is not a subtype of integer, or integer is not a subtype of string. Well, neither one is a subtype of each other. Anyway. And then the last rule is sort of the longest, but it's basically the same as the beta reduction rule from before, just now we can have multiple arguments. So the way it works is if the definition of M in C returns type D, we don't care about the return type, but it returns type D, it takes arguments AX and its body is E, then calling this method is just evaluating E, but with all these arguments. So W are the arguments substituted for the X's, the names of the arguments. And then we also substitute ourselves, this constructor value for this. So when we do like this dot, field in the body of the method, we know what this is. Okay. So other than this part, it's basically just a beta reduction a bunch of times. And then this is something you need to get sort of the real classes. But if there are any questions, please let me know.
I guess like E method still doesn't really make that much sense to me. Mm-hmm. I don't know like what part to point to.
Okay. Well, I have an example, so maybe that will help.
Okay.
If it doesn't, let me know. So here's a very simple program. This is like an actually complete program with slightly different syntax because I had to save space. But so we have this class called pair. It has a left thing and a right thing. We can get the left, and we can get the right, and we can set the left, and we can set the right. You'll notice that setting left and right really returns a new pair. It doesn't really set, so maybe that's the wrong name, but it's not CS126. So. Anyway, and then our program is down here at the bottom. So we create a new pair with 0 and 1, and we set left to 4. Oh, well, we want a screen. Anyway, here's a shorter version without casts. So we create a new pair of 0 and 1, we set the left thing to 4, and then we get the left thing. So it's going to be 4. So here's sort of the evaluation of it. So we start off here at the top, step 1 perhaps. Here's this thing, looks like a gamma. Step 1. So the first thing we do is we evaluate this method call. So if you recall the definition, or here it is, yeah, the definition of set left is returns new pair. The left thing is new left, and the right thing is this dot right. So we expand that body out into this thing. So 4 was the new left, so that goes into this spot here. And then this thing in the front, the new pair 0, 1 is this. So and over here where it says this dot right, it now becomes new pair 0, 1 dot right. And then we evaluate the arguments of this constructor. So 4 is already evaluated. New pair 0, 1 dot right evaluates to 1 because that's the right thing. And then we have new pair 4, 1 dot get left. The body of that is this dot left. So there's no arguments to get left, but we do have to substitute no pair 4, 1 for this. So this dot left becomes new pair for one dot left, and then new pair for one dot left becomes 4. So does that help?
I get the evaluation, but like, and I get how the, like, abstractly how the E method rule is being used, but like, I guess I like not the specifics, like the expression for the rule.
Yeah, I'm slightly confused by some of the notation, the definition as well. Like, I can substitute get the idea that you're just like substituting the values because it's like beta reduction, but like I'm confused about like how the actual definition is written.
So, well, okay. Is the top is the premise part fine and just the bottom is not clear, or?
Like, I feel like I'm not exactly sure how to read this. Like, I probably could if I had the rules, but like it's hard to like remember how to read everything.
Okay, so well, so just starting from the very basics, if everything on the top is true, then the thing on the bottom is true. So the thing on the top says when we look up method M in this class C, its definition is this thing on the right. So for example, if I do, maybe it would have helped if I actually defined method properly, but so if I look up in pair, let's say I look up get left because it's short. Get left. So this equals, object, object get left, return this dot left. So I mean, it just literally gives you back the function definition with its name, its arguments, return type, and the body. So this just says when I look up method M in class C, I get this thing on the right hand side. So basically what this is saying is that the method M has to be defined for me to call it. And then the bottom part is a little bit more complicated. So we have this new C, and the fields have values V. So if we go to the pair, the V's will be one thing for the left and one thing for the right. So, like here it's 0, 1 to start out, and then, evaluates. So we're calling method M, and the arguments we're passing in are W. So W are also values. Like in our example, when we're calling set left, it's 4, but it could be like an empty list for get left too. And the way we evaluate that is we take the body of the method, E, and we go, so for each argument we're passing in W, so like for each W1, W2, W3, we substitute that for X1, X2, X3. So it's like, I'll write it here. Yeah. Okay. So we have, so this thing is E. So we have new pair and then we're substituting. So the first argument is 4. So substituting 4 for new left and new pair 0, 1 for this. Sorry about the handwriting. Okay. So this is, this case is only one argument, but this is what the bottom of the rule looks like for set left. If there are more arguments, you do more, you substitute W1 for X1, W2 for X2, W3 for X3.
Okay, yeah,
I don't know if that helps, but I hope
yeah, it's pretty clear now, I think.
Yep, pretty clear.
Okay, so move on from evaluation to type checking. So type checking is, well, somewhat, is pretty similar. The sort of basic type checking judgment is still the same. Right, gamma proves E has type C, or in environment gamma, E has type C. To say that E has type C in this environment gamma, C is going to be some class. The variable rule is exactly the same as before. So if X has type C in our environment and we use X, it will have type C. when we do a field lookup, we have to do first check. So we're getting field fi from some expression e. So first we make sure that e has, or we check what type e has, and make sure it has some type. It has some type C, which is the class it is, and we look up the fields of C, and we get some list of fields, and the type of fi is the ith thing in this list that we looked up. So, you know, our original, back in the pair example, so like left is like field 1 and right is field 2. The type of both of them is object, but that's what the Ds are. Okay, so now we have these rules, which are again, these are basically the rules for functions and pair constructors that we had before, but now for n-ary functions take n arguments and n tuples. So the first rule, it got written like this because there's too many premises to fit on one line, but this is the same as before. It just means that, you know, all three of these things, you know, 1, 2, 3, all three of these things have to be true. The vertical, just ignore it. So we're calling some method m on some expression e, and the arguments we're passing in are this list of e primes. So first we check e has type C. Then we look up this method m in the class C to get whatever the method definition is. So we need to check that the arguments we're passing in have the right type, and we need to check that we need to check that the method things we're passing in have the right type. We'll check the actual method later to make sure that this return expression actually is the right value or the right type. But so by the declaration of m, it returns something of type D. So this method call is going to be a value of type D. And then all we have to do is check that each one of the e primes has the right type A. So this is sort of shorthand for like gamma proves e prime 1 has type A1, and gamma, like and, and gamma proves E2 has type, E2 prime has type A2, and so on, for however many arguments and however many arguments there are. And then for a new, we use a similar idea. So when we call the constructor for class C and we pass it a list of arguments E, we have to look up the fields of C. So we're supposed to give it one expression for each field. And we check that the expressions we gave it actually have the right types. Okay. And then the last thing for expressions is casting. So this is very important because without it, we don't have like generic programs. So we can't, if you recall from the earlier example of the factorial program, we need to cast between integer and object a bunch if we're going to have if statements, unless we have like one if statement class for every kind of type, which I guess we could do, but that would be annoying. And in general, it's not really going to work. And then, so you have, yeah, so I'll start with the rules first, and then I'll talk about the stupid cast. So first is upcasting. So if we're casting an expression E to type C, we check that E has some type D and that D is a subtype of C. And if that's true, then the cast is fine and you can do it. Upcasts always succeed. Just like casting like integer to object or something, like that can't fail. But we also have downcasts. So downcasts is the other way. So if you're casting object to integer, which can fail because your object may be an integer, but it may be a string or maybe a pair or whatever. So it's basically the same rules before, except we've flipped the order here. So instead of saying that we're casting something of type D to C, and C is a super type of D, and now C is a subtype of D. And the last thing is a stupid cast. This is actually what, if you look at the paper, this is actually what they call it. So the only reason you need this is because of sort of a annoying thing that during evaluation, you can run into this case, and to prove the theorem that the type system works, you have to be able to handle this case. So this case is basically, this is if you were to do something like, so you have the string test, you cast it to object, and then you cast it back to, not to string, to like integer or something. So this will not work, but so it type checks it first because I cast test to object, which is a super type of string, and then it casts object down to integer, which is a downcast, but it's still fine. It could fail, but I don't know if it will or will not. So this type checks, but then as it evaluates, you'll get to a point where you're casting test to int, which will not work, but we still want it to type check in this particular case because it lets us prove the theorem, basically. So the idea here is if E is type D, but D is not a subtype of C, and C is not a subtype of D, so these have no relation to each other, then you can still do the cast, but you get this stupid warning. So basically, if you type check your program and you have a stupid warning, you should not run your program because it will definitely not work. But there's no way to prevent it sort of at runtime. I hope that makes sense. Whoops. Okay. Anyway, yes, and the last thing we need is to check whether a method's declaration agrees with its body. So if I say this method returns an int, does it really return an int? And this rule is, again, it's probably the most complicated rule we've seen so far, but don't worry. So again, we have these three premises. And really, we need to check sort of a couple things, or two main things. We need to check the return type, or the return expression has the right type. And we need to check that if this method also appears in some superclass, then we're overriding it properly. Because you wouldn't want to have, a method in like a superclass that returns like an int, and then you override it with a method that returns a string. That would be bad. So first we check, so given the arguments, you have a1, x1, a2, x2, et cetera, up to a1 or an, xn, and this has type C, then we check that E has type D, which is the return type of the method. So that's one important check. This is checking that the expression evaluates to the right type. The second check isn't really a check, it's just looking up the class in the environment to see what the superclass of C is. So C extends C prime. And then the last thing is we say, so if this method does appear in C prime, this is a little bit of abusive notation, but I hope you forgive me. So if this method appears in C prime, then we look up the method in C prime and we make sure that it has the same return type and same argument types. So here we have D and AX. And if all this is true, then this method is okay in C. This is the thing we're checking. This means that it's okay in the class C. It's okay as a definition or method declaration in the class C. And to make sure that a program is good, we need to check this for every single method. And then we need to check the main expression to make sure that it's also well typed. And then we can run the program. Okay. So here's our example program again. We will type check some of it because I don't want to, technically type check all four of those methods, but I'll just do one. So here's the proof tree that type checks the set left method. Again, I apologize for all the abbreviations, but I'm using setL and this.r instead of set left and this.right because they were too long. So to check that this method is okay in pair, the class it's defined in, we need to apply this T method rule. So the first thing we're going to check is this. So given the arguments and that this has type C, we need to prove that E has type D. So C is pair, D is pair, E is the method body, which we'll see in a second. I just want to comment that we don't actually have to do any of these things because it inherits from object. There are no methods in object, so we don't need to check 2 or 3. So we're just checking the one thing. So to check the body, so this is E. So to check the body, we need to check that given the arguments, so object X, this, whoops, that should be the other way around technically. So given these arguments and that this has type pair, we need to check that this E also has type pair. So to do that, we need to use the new rule, the constructor rule, which checks that the arguments that we pass to the constructor have the types expected in the fields of the pair class. So the left and right fields both have type object, so we just need to check the x is type object and this .r has type object. Okay, so x is type object because that's just in the environment, so that's easy. Application of the variable rule. Checking this .r has type object means we need to do a field lookup, which means we need to check that this has type pair. And once we know this has type pair, we know that this has a right field and the right field has type object because that's the declaration of the right field. So there's a little bit of stuff skipped here, but I hope this makes sense. And then the last thing we're going to do with this is we're going to check set left, or not set left, that's not right. We're going to check the like main expression. We want to check that it has type object. Doesn't matter what type it has as long as it has some type, but we happen to know it's going to be object. I'm also going to pretend I have an int rule that lets me do like this because we don't really have ints, but you know, just pretend. So we want to check that the main expression has some type in the empty environment, which I'm going to write with this dot. You can also, a lot of people also use the empty set symbol, but I'm using the dot for this one for some reason. So yeah, so at the top level, this is a method call. It's a invoke, because the top level thing is this get left. If I parenthesize it fully, you'll be able to see, but I think you can see now. Anyway, and then, but that invocation we're doing on another method invoke of set left. And that we need to check that the argument has type object. So this for has type object, which we do with this you sort of make believe int rule. And then we need to check that the thing that we're calling it on, which is called the receiver, is a pair, because the pairs have this method called set left. So to check that this new is really of type pair, we need to check that both of the arguments to new match the types of the field, so both objects. So here I've used notation even more to make it fit, which is just to say that both 0 and 1 are objects. So given that they're both objects, we can prove that new pair 0, 1 is a pair. And then given that new pair 0, 1 is a pair and 4 is an object, we can prove new pair 0, 1 dot set left 4 is a pair. And given that, we can prove new pair 0, 1 dot set left 4 dot get left is object. And that means our program is well typed and we can run it. Okay, so yes. Okay. Yeah, so I'll say one more thing about Featherweight Java, I think, which is, so before we had progress and preservation, we still have progress and preservation, but they're a little different. So, well, one, they call it subject reduction. I don't know why they called it. I mean, I guess it's an old paper, so whatever. Anyway, so theorem, the subject reduction theorem says if E is well typed and E is well typed and it has type C and E evaluates to E prime, then E prime is well typed with some type C prime, where C prime is a subtype of C. So as I evaluate, I may get more information. So I may think, oh, this thing is an object at first, but then later find out actually it's an int, right? But that's fine as long as int is a subtype of object, or whatever I evaluate to is a subtype of the thing I started out with. So we don't have to have the exact same type, but it has to be compatible in this way. So that's one little additional complication to preservation. Here's the somewhat more complicated progress statement, which is, so again, E is well typed. It's also closed, so it doesn't have any free variables. So then either E is new C for these values, so it's fully evaluated, or whoops, this is actually one more case, which is that it keeps evaluating. But so, or E is stuck at a downcast, which means that it looks like, there's some cast, but C is not a subtype of D, so we can't actually do the cast. So it's like casting a string to an int or something, because you could have a well-typed program that does end up doing this, or this is the missing third case, or E evaluates to E prime for some E prime. So either we're done evaluating, we're stuck at the cast, or we can keep evaluating. So it's almost the same as the previous progress, but now we can get stuck.
Isn't the purpose of like progress to make sure that like we can run the program, or is that not true?
Yes, no, that's true. That's the purpose of progress.
Okay. So why would we allow the case that E is stuck at a downcast?
Because we basically can't prevent it. Because you can't like analyze like if you want to be able to come up with a type system that's strong enough to prevent it, basically, because well, maybe you could, but this type system isn't strong enough too, and neither is Java's, right? Java can fail at bagcast too. So the point of this language is to model some part of Java. So they wanted to keep that in. It's also hard to avoid, just because the nature of how casts work means that you can get stuck at downcasts. So you need something stronger to really prevent it from happening. But so instead of getting this, super nice, like either we're done evaluating or we can keep going, we have a slightly less nice, but we can't just fail like any which way, right? There's one very specific way we can fail, and that's better than being able to fail anyway. So,
okay, gotcha.
Yeah. Yes. So there's an extension of Featherweight Java that has generics. This is sort of the generic version of the program we've been working with. We can talk about this. I'm not going to talk about it now. I don't have slides for it anyway, but I'm not going to talk about it now because we have like 5 minutes. Yes, we're going to talk about the next thing we're going to do. So yes, we have Featherweight generic Java, FGJ. It's simply more complicated than Featherweight Java, but we can talk about it, especially now that we have talked about Featherweight Java. But we don't have to do that next. So next week is going to be Dylan's presentation. And then week after that is Thanksgiving break, and then Thanksgiving break. Well, because we're doing power meeting on weekends. So Thanksgiving break kills 2 of them. Then we have 1 more meeting after that, and then finals. So we have basically 1 more topic to choose. Because I assume we're not going to meet during finals. So yeah, so we can do Featherweight Java or Featherweight generic Java. We can do other more like type theory things. I mean, not more type theory, but more like, I don't know, like functional lambda calculus things. So like recursive types, which lets you define lists sort of in the Haskell style. I don't know if you can do like data list A is nil or a list A. So you can use like the type in defining itself. You can do higher kinded types, which is gives you like type constructors like lists. So I mean, this actually I guess uses 2 things. So you can sort of parameterize things on the kinds of the types. So you can have types, you can type constructors with 2 arguments, etc. There's another thing Haskell has, which makes it nice because you can define things like monads and stuff. But we'll talk about that probably exactly. Or I can just pick something I think is cool. And we can also do something that's not type theory. There's lots of programming language things that are not type theory. But I'm happy to just do more. Anyway, talk about like compilers, interpreters, like implementing these things, program verification, proof assistance. So yeah, what do you guys think?
Personally, I'm probably most interested in like the bullet points under some other type theory topic. Yeah, I'm like less interested in like Featherweight generic Java because I don't know if I'm not no reason particular, just other stuff just seems more interesting, I guess.
Yeah, that's fine.
Yeah, I would agree. Like, I guess for me specifically, I would be interested in like higher kind of types, and well, also like maybe compilers, just to get a little bit of like non-type theory stuff. But yeah, I'm cool with anything.
Okay, cool. Well, in that case, it seems the intersection is higher kinded type, so we'll probably do that. Yeah, you can see Timothy's logo compiler. And yeah, last thing I want to mention, yeah, so I'll keep doing this next semester, or it will keep happening next semester, but then I will graduate. So if you guys are interested in taking over, go on your resume or something. So let me know. You don't have to like, I mean, you can talk about whatever you want. It doesn't have to be the same things. But if you want like, I don't know, if you're interested, let me know. If you want like advice on stuff or like, you know, like you're like a talk or something, I can like help out. But I would like to keep it going after I graduate. So, you know, think about it. Yeah, and that's all I have. Actually, I timed it right this time. So, wow,
Oh, nice.
huge.
That's on the clock.
All right, cool. Yeah, you guys have any questions or anything else you want to talk about? Or
I guess nothing